Hello everyone, welcome back to a new lecture in a series of lectures on classical mechanics, which is meant for master's students majoring in physics. And today we are going to have lecture number 5. So let us now start with the place where we have left out in the last class, namely the mathematical definition of a linear dynamical system. And we have the equation that was written at the end of the class, namely, so the way in which we are going to mathematically represent a linear dynamical system will be like this. So that is, it is well known that we have seen this particular thing in the last class. Especially, this has to be subject to the condition that suitable initial conditions are provided. If the initial conditions are not given, or if it is not available, then we will be unable to solve the problem completely. We can of course get some general solution, but that is not the solution in particular. So a specific condition you will have to provide. Otherwise, we will be only giving the general solution, which means that the trajectory cannot be determined. The trajectory will be what you call the family of solution. So I think the terminology should be familiar to you. So therefore, let me explain here what is the meaning of family of solution. If you are going to consider this kind of a simple differential equation, dy by dx will be equal to, let us say that I will write down that this is actually 3 times x. This is the very simplest differential equation, which means that the solution requires the integration on the both side. So I will be getting y will be equal to, if you integrate on the right hand side, we will be getting 3 times x square by 2. Then we have a plus 2. Okay, this c is a constant of integration that you already know, that every time you perform an integration, one arbitrary constant will be automatically added. Okay, and the reason why it is added, of course, you should know. Suppose if you differentiate this particular relation, so let me now show the explanation in terms of a white color cursor. Yes, so now you have this particular expression y. If I differentiate this, what will happen is the constant will disappear. So therefore, you will be getting back the previous expression. So therefore, having a constant here will not affect by the differentiation, and therefore any constant is allowed. That is what we mean to say arbitrary. Arbitrary constant means any constant. That is the meaning. But now, so what happens is, so because of this reason, we call this particular solution the one parameter family of solution. Now this is the mathematical language of the solution. So what I mean to say is, this particular c is known as one parameter because it is only one number. C is a number. If you have c and d, then we can say that it's a two parameters. So let me therefore write down, this is one parameter. Parameter means something that you can vary, but still it is a constant. It's a number, that's all about it. But what is a number means, it can be 5, it can be 23. So 5 and 23 it can change, but still it is not a variable, but it is a constant. So that is the difference between variable and a parameter. So variable means it will vary smoothly. Smoothly means continuously. It can take all possible values on the real axis. That's the meaning of variable. Parameter means it will take certain number, and that particular number will be a constant. It can take either this number or it can take that number. That's the meaning. So that's the difference between a parameter and a variable. If you differentiate a parameter, it goes to 0. If you differentiate a variable, it can't go to 0 if you are differentiating with respect to that variable. So that particular distinction should be clear to you. Now, because c happens to be one parameter, this name of the y, what is the name for this particular y is, this is known as one parameter solution. Solution to the original differential equation, which is given by equation number 1. So let me say that this is very equation number 1. So this is the technical language, I mean the mathematical language for the solution. Instead of simply say that it is a solution, people say, to be more precise, people say that it is a one parameter solution. By that, what all we mean to say is that the solution contains one arbitrary constant. That's the meaning. So, which means that if you want to plot, for example, if you are going to plot a graph for this, and that which means that x direction is like this and y is here, and forget about this 3 and 2. There is a 3 here, there is a 2 is there. So, okay, some two numbers are there, but finally, the y is going to be varying like x square. So, we have a graph like this, y is proportional to x square. So, which means it is supposed to be parabolic in nature. So, we can plot like this. Because of the parabolic nature, we can plot something like this. So that is how the solution will look like. Now this is what is known as like. So this is what I am reading like here. So y varies like x square. That means the behavior is of the form x to the power 2, namely the quadratic behavior. But however, that is not the exact graph. That is what I mean to say. I want to tell that point. Exact graph is different, and then a graph looking like is different. Now why you can't say that this is an exact graph is, you didn't tell me the value for C. Suppose C takes 7, what will happen? If C takes the value 7, then this graph has to be shifted here. So let me therefore draw the graph in another color. So here I will show that I can draw the parabola will come here, for example. And in that particular case, this particular point can be 7 here. This particular point. That means the parabola will be shifted up here because C equal to 7. So I am considering the situation for C equal to 7. That means only when you tell that C equal to 7, if you fix that, I can also fix clearly what is the parabola or what is the exact solution. If that is not available to you, what all I can say is the behavior will be parabolic. That's all I can say. It can be the white color parabola in the dotted line, or it can be the yellow color parabola. It can be any other parabola here. It's only parabolic in nature. That's all you can say. But we can't tell what is the exact solution. And because of that reason, we give the name one parameter solution. And therefore, coming back to our original discussion here, this being the coupled differential equation, so that is the coupled differential equation that you are going to have, we need to have a suitable conditions are required. Now, the suitable condition is the initial conditions that are required in order to eliminate the arbitrariness. Arbitrariness means you should not say that the behavior is like. Instead of that, you have to say that the behavior is exactly this. Okay, that means you are providing the suitable initial condition. Initial condition means you already know that at time t equal to 0, you have to specify what is the value for x, what is the value for y. That is the meaning of that. So because this is there are two first order differential equations are there. Each first order differential equation will require one constant, and therefore one condition is enough. That is what we mean to say. So there are two first order equations are there. Therefore, we need the initial. I will write IC as the initial condition. I'll say that we need one initial condition, and that will be the second initial condition. The second initial condition will be there. If that is not given, yes, that's what I'm once again telling, that exact solution cannot be given, but we can only provide a general solution. This point is very important, because if you are going to solve some problem, you have to be more careful what is given in the problem, what is that you want to do. So that is important. And coming back to this particular terminology, one parameter solution is possible. If you are going to have a second order differential equation, then the name is known as two parameter family of solution. It's a family. Why it's called a family is this yellow color graph is one parabola, this white color dot is another one, this yellow color is another one. Like that, you can draw any number of parabolas can be drawn for different possible constant values C here, this C. So if you change the value of C, all possible values, then you can draw infinitely many parabolas. And because you are going to have several of the parabolas, the name is known as family. So therefore, let me write down that this is a one parameter. I will insert a word here. So this is a one parameter family of solution. So this particular terminology is being used by mathematicians. Of course, my explanation and then the definition and explanation will be precise and accurate to the literature of mathematics. That's what I'm little bit more careful in defining certain terms in such a way that they are mathematically accurate. So rather than saying some general words, we better use more accurate words which are recommended by mathematicians. So that is what I am exactly doing. So for the first order differential equation, we have one parameter family of solution. And for this second order differential equation, very second order differential equation, this is second order differential equation. So once again, I'll show you that whatever you have written here, this is a second order differential equation. But second derivative is not visible to you, right? So this is a first derivative and this is another first derivative. That means you are going to have two first derivatives. Two first derivatives are equivalent to single second order derivative. So this concept should be familiar to you. Otherwise, I will explain now. Okay, before explaining, so let this particular idea be clear to you. So the family of the solution is very important terminology. One parameter, two parameter, that is a generic name that is used to the solution. Okay, coming back to this, let us once again summarize what is the statement of the problem. A linear two-dimensional dynamical system is characterized by a set of coupled differential equation given by this, namely equation number 2, subject to, so this is the extra thing that I am telling, which I did not tell in the last class, subject to suitable initial conditions. Suitable means the number of initial conditions should match to number of requirements. That is the meaning of suitable. The second thing is the suitability can be in different ways. Either you can provide x comma y values or you can provide x comma x dot values. So sometimes some other combination can be given. Ultimately, it is a matter of two initial conditions. That's the meaning. So these 2 points are clear. Okay, why do you want this initial condition? That's clear. And then I will also next explain why do you want to use the word initial here. Because usually when you are studying or already you might be familiar with the two names. One is known as the initial condition. The another one which is quite common to you or which is familiar to you could be a boundary condition. So you may think that whether we have to use only initial condition, if that is the terminology that we have to use, or can we interchange them? Can we say that it's boundary condition? The answer is no. You can't interchange them. The meaning of initial condition is different from the meaning of boundary condition. Initial means it is representing time. That is very important. The word initial itself represent that it is going to represent time, and therefore initial means we are going to start something. If you are going to start a chemical reaction, then you have to say that at time t equal to 0, you have to provide. So how much amount of the substances that you have taken, all those things when you are going to start the experiment. So automatically the point is that the meaning of initial is at t equal to 0. That is the meaning of initial. But this particular meaning will not come when you are using boundary. So boundary means some edge. Suppose if you are going to have a room here. So if this is your room, okay, and then what is meant by boundary means these are the walls. These are the walls of the room. So these are known as the boundaries. So boundary means that is the place where something comes to an end. So if you go out of that, you don't have a room. You come to a open space outside. So what is going to distinguish from your room and the outside world is the wall. So that is the place where your room or your house comes to an end. You are then going to outside. So that particular line which separates the outside world from your house is the wall, and that is known as the boundary. So this particular term boundary, so condition means on that wall what is happening. So you have to provide. So on this wall, you give me what is x, etc. You give me what is y. You give me what is x dot. Whatever value is available for that particular problem, you have to provide it. That is the meaning. On the wall. On the wall is what is known as a boundary condition. And now you can easily tell, can you interchange them? You can't interchange because totally it's a different concept. The one, this is representing with respect to the time. This portion is representing time, whereas whatever discussion that we have done here represents a physical boundary. So therefore, boundary condition and initial condition, the word cannot be exchanged or the word cannot be interchanged. They have completely a different meaning. So how the appearance will look like in mathematically, we say that we can easily say like this: the temperature of the wall at x equal to 0 equal to 30 degree centigrade. The temperature of the wall at x is equal to 10 meters equal to 100 degree centigrade. For example, if I am going to bring an x-axis, let me bring an x-axis here. So I'm going to bring an x-axis here like this, and then it goes like that, and bring the y-axis and keep it here. If you do like this, then that will be 0, and let us say that this is your 10-meter distance. So what it means to say is that on this particular wall, so you have a wall here. So on this particular wall, I am maintaining 30 degrees centigrade on this left side wall, and I am maintaining 100 degrees centigrade on the right side wall, because the right side wall is the one which is at the 10-meter location with respect to the coordinates. Therefore, I am maintaining 100 degrees centigrade. That is what we mean to say. So this is how the appearance of the boundary condition will be looking like. But the appearance will be looking here in a different way. It will look like this. The temperature of the rod, whatever, let us say you are going to consider some rod or wall, whatever it is, at time t equal to 0 is 30 degrees centigrade. The appearance of the initial condition will look like this. The temperature is capital T, at t equal to 0 is inside bracket. Here, temperature is capital T, at the location x equal to 0 is inside bracket. So therefore, boundary conditions and initial conditions are completely different. They cannot be interchanged. Now there is one important thing that is required. Now, how do I know whether a differential equation requires a boundary condition or an initial condition? How do I know that? How do I know whether a differential equation requires initial condition or whether it requires a boundary condition? Of course, that is very simple. If you have a look at the differential equation, if the differential equation looks like this, dy by dx equal to 3x, if this is your problem, for example, then automatically what is an independent variable? Independent variable is the one that you are going to write in the denominator. X is there. Since x is going to represent the position, then automatically we will be requiring boundary condition for this problem. If your problem is like this, for example, solve, I have a different problem like this, dy by dt will be equal to 3t. If this is the problem, then t will be representing the time in the given problem, and therefore we need the initial condition for this problem. So in the given statement of the problem, first of all you have to understand what is the independent variable for that problem. Suppose if you are going to have two equations, for example, let me write down another equation which has a combination of time derivative as well as space derivative. I will show another example. I will show that the equation looks like this. Dou square y by dou x square is equal to some alpha times dou y by dou t. I have an equation like this. So what do you understand? You understand this. The independent variable is the one which is there in the denominator. But there is also another denominator here. So therefore, this particular equation clearly tells that I don't have a single independent variable, because one independent variable is x, the another independent variable is t. Both of them are there in the denominator. Therefore, x comma t will be the independent variable. Now, what is a dependent variable? Dependent variable will be written in the numerator. As you can see, in the numerator you don't have two different things. You have the same thing. If you have two different things, then it is either it is a coupled equation or that you have written a wrong equation. That's the meaning. You cannot have two different things. Like this you can't write dou square y divided by dou x square equal to, let's suppose if I say that alpha times dou z divided by dou t. If I write like this, and if I say that this is the only equation that you have, then this is wrong. Why it is wrong is, Y is okay, I agree that Y is a dependent variable and X is independent variable, T is independent variable, all these things are okay. Alpha is a parameter, constant, everything is fine. Then the question comes, what is Z? You can't say that it is dependent variable. Suppose if you want to say that this is a dependent variable, then it should be coupled. You have to fill another equation here. If the another equation is not there with respect to Z here, and if you say that that is the only equation, then this equation is wrong. So that is the point I am trying to say. There is a Y here, there is also a Y here. So this is fine. A single independent variable, single dependent variable is there in the numerator, and that's what you have to write down, that Y. Therefore, Y is a function of x comma t. That is what you say mathematically. We say that Y of x comma t. Y of x comma t is the style in which we read it usually. Y of x comma t means Y is a function of x comma t. That is the meaning. So is the solution. Is the solution to the above equation. That's fine. But what about the initial condition and the boundary condition? Do you require any one of them, or do you require both of them? So the answer is clear that you need, because there is a time derivative is here, I must, or you must provide one initial condition is required. That is first thing. Second thing is, you also have the second derivative in the space. So therefore, I will write down here only one initial condition is required, because it's a first derivative, or only one derivative is there with respect to time. But if you are coming to the space here, it has a two derivative. So every time you are going to perform with respect to space, two integration has to be done. Only then I will be getting Y. Therefore, two constants will come into picture. Therefore, I need two boundary conditions. I am now using the boundary condition because it is with respect to X, and this is required. So totally how many boundary conditions and how many initial condition is required? One initial condition is required, plus, this is important, I am not saying or, okay, not either or, combinedly one initial condition is required, plus in addition to that two more boundary conditions are also required. So if you are going to provide all these things for this particular equation, let us say that this is equation number 3, then we can solve that particular equation. Otherwise equation 3 is not solvable. So basically, by this discussion, what did you understand is, you understand what is the meaning of initial condition, what is boundary condition, what is the difference between them, and how do you know which kind of condition is required for a given problem. All these things can be easily found out if you are going to have a look at the equation. If you give a look at the differential equation, you must be in a position to tell what conditions are required. At least how many number. I'm essentially talking about how many conditions required. What is the type of condition? Type of condition means initial boundary. How many is number, 1 or 2 or 3? That depends on how many derivatives are there. So this is the basic thing. Hopefully you must be, many of you may be already familiar, because you have studied certainly something on differential equation. So coming back to the original to our problem, how this equation is looking like. So this equation, both of them are looking like a first derivative with respect to the time. So therefore, how many conditions are required is, we need two conditions, because one condition is required for first part of here, the second condition is required for this. So here I have written suitable. So what do you mean by suitable here? The meaning is that we need two initial or boundary. Initial. Because why do you want initial? Because all the independent variable is t here. That is the reason. So time derivative is there, and therefore two initial conditions are required, and that is what is the meaning of suitable here. Okay, so these are the basic things. As you solve the problem, you will have to observe when a particular question is given in a question paper, you have to pay attention to what is provided to you to solve the problem, and then check whether these conditions are given to you. If some of them is missing, probably only general solution can be given, but exact solution or a particular solution cannot be given. So this is the meaning. So okay, so with this is fine. Now let us proceed further to what to do with this particular equation in the next step. Before that, I would like to erase this particular portion so that I can go to the next page. Okay, so right now, so ultimately we are now back to the original discussion of the two-dimensional linear dynamical system given the initial condition, and it is a usual practice to abbreviate x at t equal to 0 by a suffix x naught. So by writing in a simple style x naught, we understand that it is the value of x at a time t equal to 0. Similarly, y naught means the value of y at a time t equal to 0. So the symbol itself will give you the explanation so that you can avoid a lengthy writing. That is the reason why we do this. Okay, so now the solution methodology, or the first step in rewriting this particular equation, is to consider or generate a vector. So you can write like this, or you create a vector. What is that you want to create is, I'll write down the vector by some kind of a capital letter. You can see that this x is different from this x, capital letter. So let us create a vector like this, which contains two elements x and y. So it is clear that these two are not same. You remember that x, this particular small letter x is not equal to capital letter x. Generally, small letter a is not equal to capital letter a. So this is the general tradition. You should not think that they are the same, because you see, if you are going to work out with more amount of equations and variables, you need a lot of variables to deal with. So you have 26 alphabets, A, B, C, etc. up to Z. But however, 26 of them are not sufficient for me, because several variables are there, several equations are there. I need more than 26. Then what to do? But there are only 26 alphabets are there. So what you can do is, you can generate another 26 if you are going to consider capital A, capital B, etc. So you have to now you have to be more careful and more clear that the small letter a is not equal to capital letter A, and so on. So by that way, what happened? Now I am having 26 plus 26. I got 52 variables to deal with. So in that way, I can write an equation like this. You see this particular equation, where you have to be careful that the capital X and the small x are not at all same. That is totally different. The capital X is something totally different. Small x is something that is totally different, completely different. Okay. What do you mean by completely different is, this x is a scalar, just a number, single number, or it can be variable, but whatever be the case, it's a single number. But capital X, you see that it contains two elements. It's a column vector. So column vector and a single scalar, they are totally two different mathematical objects. That is what I mean to say, that x is not equal to x. They are not at all same. Nowhere connected. You should not even think that they are related and connected. Even that is not so. They are completely different. That's all about it. And so 26 plus 26 is 52 is fine. But even this 52 is not sufficient for me, because more equations are coming. I need more variables. I need more suffix. Then what to do means, then only thing is that you have to come out of English and go somewhere. So people traditionally go to the Greek letters. So go to the alpha, beta, etc. Okay. So if you see alpha, beta until zeta, the last letter, how many are there? If you see, count to 24 will be there. So total number of Greek letters are 24. So already you have a 52. So you got 52 plus 24. That many variables are now available for you, so that you can write your equations in a very nice manner. But however, as the equations go and they get complicated, what happens? Even that 52 plus 24 is not sufficient. Then what will happen? You have to create another 24 of them to create capital letter alpha. So this is capital letter alpha. Okay. In the A here, this horizontal line you remove. So if you remove this horizontal line, then this is the alpha, capital letter alpha, and capital letter beta, of course, capital gamma, capital delta. This is the small letter delta. Okay, this is capital letter delta, etc. All capital letters will come. So I can add another 24 here. Like this, you can create more number of variables as the demand comes into picture. Even this is not sufficient. So then what will you do? You put suffix. Okay, you keep a suffix here, or you keep a superscript here. Okay, this is a suffix, for example, that is a superscript. This is not x square. So there is another trouble. There is another thing that let us not go into the detail now. this is a superscript 2, not compulsorily square. Okay, that is also possible. So when time comes, I will explain this matter. Okay, let us now go back to your original discussion, and then I will erase some portion of the board. Okay, so create a vector with a letter capital X equal to x comma y, which happens to be a column vector. So then what happens is, if you are going to create, then our original equation. So let us call the original equation by equation A. It's a coupled equation A. Then what happens is, then the equation A becomes like this. Equation A can be rewritten. How do you rewrite is that you put a column vector and then write down dx by dt. And then, okay, let me avoid this dx by dt notation because you are now comfortable with the x dot notation. I will write down that this is x dot. So this particular thing, and then this will become a y dot. So that is a column vector. So that will be equal to, once this is a column vector, you can rewrite this equation A as a product of a matrix and a vector. So you can now fill what will come. So this x is there here, there is a y here. So I will write that x here and then that y here. If it is the case, I have to generate ax plus by. So in order to generate in ax, I have to write a. So that a times x. You know the matrix multiplication, right? Matrix multiplication, you have to bring a times x. Then there's a plus. That plus comes naturally. Now you understand why the matrix multiplication, you add them. So ax is here, then plus by. So in order to bring this plus and by, here you have to put a b. And naturally this becomes c and this becomes d. So therefore equation A has been rewritten in a matrix notation. Now you see that this is a time derivative column vector and this is the one without time derivative column vector, and here you have a 2 by 2 matrix is entering into picture. So therefore this is the most comfortable way to solve the equation number A. Of course you should ask the question, why do you want to write the equation in the matrix form? The reason is we are interested to solve equation A, and the matrix method provides a comfortable and convenient solution. Otherwise it will be quite difficult to manage both of them together. Now I will emphasize the word together. That means coupled. The two equations that is there, yesterday I have explained why it is coupled. The set of equations which are written in the bracket here is coupled. That coupling is taken care by the matrix. You see that already its bracket is there here. The big bracket is there. So therefore matrices denote certain things that are coupled in nature. A set of coupled equations go together. That together is what is known as the set of all numbers. Whether it is 2 by 2, 3 by 3, whatever it is, the entire thing will go together. You can't remove certain numbers from the matrix and then do something only for that number. Okay, when you want to perform something, you have to perform the operation on the entire matrix. So therefore the togetherness is already taken care in the matrix method, and therefore rewriting in the matrix method gives you a powerful method to get an idea of the solution. Now let us not go into the solution methodology, but I will write down the important point here. Now the solution of A, or I will write down the solution to equation A requires finding or determining the. So this is the thing, that is, if you want to solve this particular equation, namely equation number A, what is that you have to do is, the first step will be to find the eigenvalues and eigenvectors of the 2 by 2 matrix. So what is the 2 by 2 matrix? Is this particular matrix ABCD. So why I am getting a 2 by 2 matrix here is because our problem is a two-dimensional dynamical system. If you are going to consider a three-dimensional dynamical system, then I will be having a 3 by 3 matrix, and once again you have to find out the eigenvalues and the eigenvectors of that. So we are not going to go into the detail of the solution, but however, if at all you want to solve the equation number A, that is, if at all you want to solve this equation, then the first thing that you have to do is you'll have to determine the eigenvalues and eigenvectors. So in a way, it gives you an idea like this. It gives an idea that our conclusion can be written like this. What is the conclusion is, The eigenvalue is also EV. Eigenvector is also EV, isn't it? So both of them are eigenvalue and eigenvector. Just for readability, I'll put a V vector like this. So now you can read like this. EV means eigenvector, and this vector symbol, the first EV represent eigenvalue, the second EV represent eigenvector. So I can write in shorthand notation like this. So our conclusion is that calculation of the eigenvalues and the eigenvector of the square matrix, because it can be a 2 by 2 matrix or it can be a 3 by 3 matrix. That's all. You can't have non-square matrices are not possible. Only square matrix you will get in dynamical system. So therefore what happens is that the determination of the eigenvalues and the eigenvectors of the square matrix gives the solution behavior. The solution behavior of the dynamical system. So this is the translation from mathematics to physics, because in mathematics you do something, no, find eigenvalue, find eigenvector. That's okay. What are you going to do with that? What does it represent? Is there anything that we can understand physically? Is that it has different application in different places, but in the context of the dynamical systems, this is the meaning. You can't consider that the same thing is applicable to every other topic. Okay, when topic changes, it's different. In quantum mechanics also you will find eigenvalues and eigenvector. So at that time it may represent something different. So depends on the problem. So for the time being, in the case of the dynamical system, we can say that, or we can make a conclusion that the mathematically computed eigenvalues and eigenvectors of the square matrix will tell you how the physical system will behave with respect to time. Will behave means, what is the meaning of behavior is with respect to time. That means as time changes, how the system will behave, or how or where the system will be at a later time. That is the meaning. If that is known to you, which means that you already solved the problem. So let me therefore give a simple illustration, because you need to be clear on the terminology. Okay, behavior. So let me tell here some example. Suppose if you are going to have a small particle or a very small ball, for example, and that is a floor. So this is a floor that you have, and then you take a small a metallic ball, because it will be very nice. It can roll easily. So if you are going to roll this particular ball, then what happens is it will travel like this. The ball will be keep moving. So what happens is that before you are going to, when you are going to start the experiment, okay, when you are going to start the experiment, then you say that at time t equal to 0, you are going to tell what you are going to specify what is the location of that particular particle. That means x at t equal to 0. That means what? This particular position. Suppose if I am going to consider that this is the scale, okay, you are going to attach a scale, for example, so you can easily find the location. So this arrow, whatever that this particular place, is the location of the particle at time t equal to 0. That is known to you, because you are only going to start the experiment at that particular point. Therefore, the value of the x at t equal to 0 is known to you. That is what is called given. Usually in mathematics, they will say that given x0. Given means how it is given, because you are only going to do the experiment, therefore you know the position. That is first thing. If you are knowing the position, then what will happen? Basically, that particular particle will be there only. It will not at all move. The particle won't move if you don't push anything. Therefore, there is something extra required over and above this. What is that required is, at the time t equal to 0, you have to tell me what is the initial velocity that you have provided. That velocity is the x dot. So I have written x dot here. If you don't provide any initial velocity, that ball will not move. That particular object or the particle or the ball will not move. It will be in the stationary. Then there is no dynamics. Therefore, when you are going to start the experiment, you have also given an initial velocity to the particle. Either you have given an initial velocity or you have given an initial acceleration. Okay, initial push. You have given a push there. So that is an initial one. So therefore, this particular thing is also known to you. So x dot at 0 is also known to you. So okay, this is given, this is fine. Now what is the meaning of saying the evolution of the system, or what is known as the behavior of the system? I am very particular in explaining this particular term. Here I have written, okay, I am explaining why we are using the word behavior. So it is the usual practice to say the solution behavior. Solution behavior means how the physical system will behave. So I want to explain you what is the meaning of behavior. Behavior, let us now understand here. That is what I am coming back here. So once you have given the initial push or initial speed to this ball, then the ball will keep moving, and then it will keep moving. And then after reaching some long distance, whatever distance possible, it will come here and then it will stop at this particular point. So there is a behavior. What is the behavior? So initially it is moving at a particular speed, then it reaches maximum speed. After that, it slowly reduces its speed, and then finally comes to stop here. That's the behavior that you have, which means that at each one of these points, you will be having the position of the particle, comma, speed of the particle. Position of the particle is directly visible because this is the scale. I will say this is the scale. So therefore, this particular point you can directly measure what is the value on the scale. So that is the position. So position is clear. Then what about this particular x dot? X dot is the speed. You have to measure the speed. So in an experiment, basically you have to measure. The measurement we will not go into detail. You are going to use some technique and then measure the speed at that particular point. So x dot is measured. X is straight away measured from the scale. So finally what happened is, I have x comma x dot will be available at each and every location. This is one location. This is one location. I have x and x dot. X comma x dot. And this is the last location. This is the last location. I have x comma x dot. You know what is the value? X is the last value. Let us say that this is 100 meter. Let us say. So therefore 100 meter will come. What about x dot? It is the last point, it came and stopped. Therefore 0. 0 is the 0 meter per second, of course. 0 meter per second. So this is the last value. So the last value will be known to you, and then the initial value will be also known to you. That is the x0 and x0 naught. That in between values you are going to determine. And that in between values, the set of all value is what is known as behavior. So you got the point. What is the meaning of behavior now? So if you are going to perform an experiment, then basically what you will be having is that at every time t, you have to measure the location of the particle, and you also measure the speed of the particle. So you write down at time t equal to 0, okay, at time t equal to 1 second, 2 second, 3 second, where was the particle located and what is their respective speed. You are going to do this kind of measurement in an experiment. And at the last you finish this. At last we don't know how much time it is, but I know that the last value is 100 meter. Okay, something is there. Okay, at the end we don't worry about it. So we are going to fill this particular table. So this is experiment. Once you have this table, this is exactly what we mean to say the behavior of the system through an experiment. Now I am not going to do an experiment. I want to do all the calculation. Then what you have to do is, you are basically going to find out the eigenvalues and eigenvectors of that particular matrix. That's what I am written here. You find out the eigenvalues. You find out the eigenvector of that particular system. That is called the square matrix. Then that gives you the solution behavior. So you don't have to perform an experiment. And your calculation gives the same behavior as predicted by experiment. So this is the meaning of the solution methodology. So you understand one thing, that the solution methodology requires determination of eigenvalues and eigenvectors of 2 by 2 and 3 by 3 matrices. Most of the time, let me tell you an important thing. Most of the time, the question paper will contain calculate the eigenvalues and eigenvectors of a particular matrix. The matrix can be 2 by 2, the matrix can be 3 by 3. But remember, even though the problem is a very well-known problem, most of the students will make mistake in either finding the eigenvalue or many people will do mistake in determination of eigenvectors, even if they find eigenvalue. The reason why it is so is that you have a tendency to neglect the topic, and you believe or you think that the determination of eigenvalue and eigenvector is too simple, or either some people think like that, or some people think that it is too elementary that you don't have to give any importance. Like that, many students are they themselves think. The reason why they think like that is the determination of the eigenvalue come all the way from your first year BSc. I think most of the time you generally study the eigenvalue eigenvector even from the higher secondary school. So what happens is, when this topic comes, eigenvalue eigenvectors, you don't pay attention to that. Okay, the method may be known or the name may be known to you, but however, remember that determination of this is the ultimate thing. If you make any mistake in the determination, your solution or the physical behavior of the system will be completely wrong. Therefore, it requires a good practice of this. And if you see the competitive examinations such as the CSIR NET or the GATE examination, you can always find some question in the determination of eigenvalue and eigenvector, not for a big matrix 2 by 2 or 3 by 3, only that. And many students will make mistake. Okay, initially you yourself won't believe, but unless you take a paper and pencil and walk out, you will be unable to get the correct answer to that. Okay, of course it's not difficult, it's easy. What I am trying to express my opinion is that practice is required, otherwise you will make mistakes. So this give an importance. What I mean to ultimately say is give importance to the calculation of eigenvalues and eigenvectors. So keep this in point. Now let us come back to this and then make one important question. So this is one question is there here. So this question is asked by one of your classmates. I think this Mishra, I think. So the question is, of course, a simple question, and the answer to this question is the direct property of a nonlinear dynamical system. So let me first tell what is the question. That in the previous class we have seen how to distinguish between a linear and a nonlinear problems. So you have two things. One is a linear problem, the other is a nonlinear problem. Now how to distinguish, or we'll say that this is a linear system and nonlinear system. How to distinguish between these two? In the last class, what we have seen is mathematically I have explained you how to determine which is linear and which is nonlinear. Okay, if the power of the dependent variable is exactly 1, then it is linear. If the power of the dependent variable is not equal to 1, then it is nonlinear. So that is what I have explained in the last class. But the question that this particular student is asking is that mathematically that is fine. Physically, if I am having an experimental setup, or naturally certain things are happening, certain dynamics is happening in the nature. Okay, for that natural phenomena or for that experimental scenario, without having any equation, how to tell whether the dynamical system is linear or not? That is the question. So in an experimental system, either it is artificially created experimental system or naturally occurring natural phenomena. For these situations, when I don't have any equation with me, how can I tell which system is linear and which system is non-linear experimentally? That is the question asked by this candidate Mishra. And the answer is, of course, going to be very simple. And also this answer is going to give you a direct definition for the nonlinear system. So let us see the answer now. Answer is quite simple one, and also important definition it's going to be. Let us come back to this particular problem in order to get the grasp. Now here you are having a ball. The ball is moving along a particular line, and then what is known at the initial time is at time t equal to 0, the position at time t equal to 0 is known, the speed at time t equal to known. These two things are known. So what means, in an experiment you are going to perform an experiment. Can you tell, this is the question, you please understand this. Can you tell at time, see 1 to 3 is there, 0 second, 1 second, 2 seconds, 3 seconds, etc. A lot of seconds are there. Suppose there is a second, 25 second is there. At time t equal to 25 second, can you tell where this particular ball will be? And at the same time t equal to 25 second, can you tell what will be the speed of the ball? Can you tell? That is the question that we ask. Okay, you are only doing the experiment. Therefore, by the way, you forget about all differential equation. We don't have any equation with us. You repeat the experiment and then understand whatever possible, and then can you tell or can you predict that at time t equal to 25 second, what is the location of the particle, and at that particular location, what will be its speed? Can you tell? By that, what you mean is, you have to understand again the question. By that, what is the meaning is, you repeat it many times and then find out. And suppose if you are going to repeat another time, if you are going to repeat this another time, then the same thing should come. That is what is the very important thing. That is, once you know that, if you are by repeatedly, when you are performing the experiment, you will be knowing that at time t equal to 25 second, you have made the measurement and you have this table. So what happens is, the same thing will happen if I repeat the experiment once again. And this is called a prediction. Prediction means what is found today or what is found now can be repeated tomorrow. And same thing will happen. That means tomorrow also, when I am measuring at time t equal to 25 second, I can clearly tell where the particle will be without doing the experiment. Because yesterday itself, I finished my experiment and I know where the particle will be. So if I am going to do the experiment today, then that in the same place only it will come. That's what I am going to tell. If you are able to tell clearly like this, and if the system also behaves like that, then the system is linear system. That's the meaning. Linear system means predictability. In terms of physical language, it is predictability. In terms of mathematical language, it is called deterministic. So in mathematics, people say deterministic problem. In physically, you say that it's a predictable problem. Okay, something you can predict means mathematically something can be determined. These two things are synonyms in mathematics and physics. So automatically, what can you say about nonlinear system? In the case of the nonlinear system, immediately you can make a conclusion that even though I have observed something today in this particular problem, tomorrow, or if I am going to repeat it after 1 hour, the same thing will not come. Which means you can't predict what is going to happen after some time for the same physical problem. So let me give an example for that. So example is a quite simple example which you can imagine and then make a conclusion about this nonlinear system. So consider, for example, let us say that you have some river, for example. You have a river, okay. So here you have the water flowing, okay, water is flowing. What you do is you make a boat, okay. During your childhood, you used to make boat, right? Paper boat. Make a paper boat, okay, and then keep it here. So when you are going to keep it here, I'm not going to give any initial velocity, right? I'm not going to give initial velocity. I am going to only keep here. Why I am not giving initial velocity is, already this water is moving. This water is moving, which means it is having already velocity. So you don't have to give any initial velocity to the boat. Or if you want to give the initial velocity, you can also give, not a problem. So the point or the experiment here that you are going to consider is that you keep the boat here, that's fine. And then same 25 seconds. After keeping the boat, after 25 seconds, can you tell where this boat will be? You have to tell the location. You have to tell the location of the boat, first point. At the same time, you have to tell what is the speed of the boat. Of course, you can measure it. After 25 seconds, you immediately take the snapshot and do some experiment and measure the position and the velocity. That is not a difficult thing. You measure the position of the boat, you measure the speed of the boat at time t. So maybe at time t, I will write down here. At what time you are going to do? At time t equal to t. Now since I am telling exactly 25 seconds, I will write here. You can always do this experiment. Okay, do this experiment and keep the number with you. So once you finish the experiment in the morning, you come in the evening and then perform the same experiment here. Can you predict now where will be the position of the boat and what will be the initial this particular speed? You can't tell, or whatever you tell, that will not happen. As you see that because this is not happening, because you should also make another assumption that this water speed is uniform. So that also you should remember. It is not the water speed is uniform from morning to evening or whatever it is. Even under that condition, this will not happen. This is one of the practical situation. Why it is not happening? Yeah, those reasons are there why it is not happening. But this is one of the practically observable one. You can always go to this kind of a scenario and then test yourself and then find out easily. The what do you call the reasons behind this kind of behavior is what is known as, let me tell you, that this is an example of a non-deterministic problem, or this is an example of a non-linear problem. Instead of saying non-linear problem, you can also say non-deterministic problem. So here, of course, we are not going to the reason why it is not predictable, and we are not going to the details. If you're going to details, then it's a different paper actually. So you have a separate soft core paper called nonlinear dynamics. So that particular paper will deal more details. So for this classical mechanics paper, nonlinear dynamics information is absolutely not required. But however, I am giving this information as a point that you should know. Okay, you should know the distinction between a linear dynamics and a nonlinear dynamics. So of course, the reasons are one of the main reason is bifurcation. So even I can't explain right now bifurcation without going into the phase space diagram. So that is why I am not going into the detail. The point to be noted in the case of the nonlinear problem is that for a given problem, that is, once you have an x0 comma y0, that means once you have the initial, let me not write the variable like this. So even though if you are going to give the initial condition, given initial condition, the problem or the solution can take two paths. The solution can take two paths. This is called a bifurcation. So what do you mean by path here? This is very important. Path is actually equivalently mathematicians will say solution to solution, which means that even though you provide a particular initial condition, if you are solving the problem, then what happens is at a particular time you can have two solutions to that problem. That is mathematically it's called two solution. Physically we say that it is going to take two different path. If it is going to take two different path, then you cannot tell where the boat will go exactly. Sometimes it will go this way, sometimes it will go that way, which means that your predictability is now out of control. You can't do anything, and such a problem is known as nonlinear problem. So experimental systems or naturally occurring systems, you can always tell which is linear and which is non-linear by repeating the experiment and checking whether the same thing happens if you repeat. If identically same thing happens every time, then it is linear. If the same thing doesn't happen every time, then it is non-linear. That's the meaning. So this is the simplest, in terms of simplest definition. We can speak like this. Nonlinear problems are more mathematical in nature. Therefore, you have to characterize them with more technical terms such as bifurcation, Lyapunov exponent. Such kind of terminologies has to be used. Then only you can characterize them. Okay. Otherwise, the only word that you can speak about is non-deterministic. That's all. It's a general word that is used to describe non-linear problems. Non-linear problems will be, many of them will be non-deterministic. an alternative way physicists like to use is chaotic system. So chaotic system is something, chaos, you are unable to predict. So that's why it's called chaotic. Mathematicians prefer to use non-deterministic problems. So this is how you distinguish based on an experiment. And mathematically, they are characterized by nonlinear terms that are present in the differential equation. Okay, these are the things that are some basics. Hopefully, you will be comfortable. We can't go more into details because we will be deviating from our syllabus. Our syllabus does not contain anything with respect to the nonlinear part. So therefore, don't have to worry. This information I am giving in order to make some answer to this to your friend's question. That's all about it. Okay, coming to this notation. Now, interestingly, what happens is after making some explanation and discussion, we have come across a set of numbers like this: x comma, that is position, comma velocity. Position and velocity you are measuring at what time? At a particular time t. So this is always meaningful. Once you fix a time t, the object will be located at some point x, and at that particular point the object will have a speed x dot. That is the meaning of this object x comma x dot comma t. Now this object is very important. So I will now come down here and then write down separately. Here I will write down, for clarity, I will write down this x comma x dot comma t. So we have been discussing, so it is very easy for you to grasp this. At any given instant of time t, there is a position of the particle, there is a speed of the particle. That is very clear. Now, quickly what we will do is, now since you already know what is meant by a generalized coordinate and what is meant by a generalized velocity, you know that x and x dot are not the preferred variables. You know what is the variable to be used for generalized coordinate will be q. So x is not preferred, we prefer q. Similarly, x dot is not preferred. Generalized means q is the preferred symbol. Q comma comma you can put q comma q dot comma time t. So the set of variables that are very much involved in mechanics and dynamics is this set of variables, that is x comma x dot comma t, which if we are going to generalize this, then we can write down q comma q dot comma t. This is the very important set of variables. So these are the three variables that are entering into our problem, and therefore we can write down a mathematical function of these two. So suppose if I have x comma y comma z, give me a mathematical function f of x comma y comma z, means quickly you can say that x plus, let me write down here, the easiest thing that you can write is x plus y plus z equal to 0. This is an example. Similarly, you can write anything, x square plus y square plus z square equal to 0. You can write anything like this. You can write any other combination, xy plus yz plus zx equal to 0. You can write infinitely many combinations. All of them are, this is a function of xyz, this is a function of xyz, this is a function of xyz. Therefore, you can write any number of or infinitely many possible combinations of x comma y comma z in order to make it a mathematical function. This is clear, right? So you can always write any number of functions. Now we are now going to write a function of, I'll write down now, we are going to write a mathematical function of q comma q dot comma t. Just like x comma y comma z, we can have some function. Of course, many are there. In that, one function is very important. Okay, out of many such combinations of functions, there exists one function of q and q dot and t, and that particular function is known as Lagrangian. So I'll write down that this is a Lagrangian function. So you understand what is the meaning of that? The three variables q, q dot and t, they are the very important set of variables to describe the dynamics. And out of the many possible combinations that you can arbitrarily write, Okay, arbitrarily means simply closing your eyes. You can always write down a combination of q dot t. But out of so many things, one function is very important, and that particular function is known as a Lagrangian function. Now, since the name of the function is known as the Lagrangian function, it is customary or it is traditional to remove the f here and then put L, because L is Lagrangian, right? So you can always say, no, f of x I can put is a function of x. Why to put only f of x? Why not g of x? G of x is also another function. You can also write h of x. H of x is also function means you should not have f. Whether it is f, g, h, anything can be there, right? You can also write k of x. So everything is function. Therefore, now here you have f, right? F is a function, that's okay. But since it is going to represent the Lagrangian, it is traditional to write L. So this is L. This is something, this is called the script L. We can write like this, or it is the so-called calligraphic letter. So you can write like this, L. L is for the Lagrangian, and Lagrangian is a function of q, that is the generalized coordinate, q dot, that is the velocity, and then comma t. Okay, so this is your Lagrangian function, and this is the one the absolute starting point of the Lagrangian mechanics is going to be this particular function. What is this function? And that is where the problem is. There exists a function, that's all about it, and there is one simple way of constructing this Lagrangian function. One easy way or one comfortable function that you can construct in order to describe the mechanics, you can construct it. But remember, that is not necessarily a single function. You can always have, mathematically you can have a large number of functions, but however, there exists one function that is going to be very useful to describe the mechanics. That function is known as the Lagrangian function. Okay, so this particular symbol terminology, these are very important, and therefore let us make this particular statement as one of the important conclusions in the today's class. So what we will do in the next class is, we will ask the question that what are you going to do with q comma q dot comma t? What we can do with that? The answer let me tell, and then further details we will see in the next class. What is the answer is, what are we going to do with the q comma q dot is, we are going to draw a diagram what is known as a phase space diagram. Okay, if you are going to plot a diagram or whatever it is, whether you call it diagram or you call it plot, or you can also say graph, whatever you name you are going to give, it is known as a phase space plot. Phase space plot or phase space diagram is what is exactly the diagram that you are going to draw between the variables q and q dot for every time. So q and q dot is the graph that should be plotted for every time. That is the meaning. So if you draw that, such graph is known as the phase space diagram. So that detail we will see in the next class. And once once this is clear, then almost you are ready to move on to the Hamilton's principle. So we are actually moving in that particular direction. Okay, fine. We'll meet in tomorrow's class.